Hi, welcome back to part 2 of nuclear medicinal chemistry. And the second part is really not so much about the medicine, but how nuclear reactions take place and what type of stoichiometry or what type of equations are we going to have. All right. And so the very first thing that we need to understand is that through the process of nuclear decay, a parent radioisotope, the nucleus of a radioisotope, will actually emit some type of radioactive particle or some type of electromagnetic radiation, namely gamma rays, and a daughter nuclide. Again, we use the word nuclide just to represent what is just the nucleus. We don't care about the charges or anything like that at this moment. And just like in any chemical equation, in a nuclear equation, we need to make sure that everything is balanced. So we're going to balance not only the mass number, which is the number at the top, A, but we also need to balance the overall number of protons or the nuclear charge, Z. All right, so both of those two numbers must be conserved in a nuclear reaction. All right, and so I have put this image here that has a couple of just little things that I want to make sure. It was missing the arrows, and then it had two small mistakes. So those of you who are looking at this from my handout, please make sure to make the correction or add the corrections. All right, this is an image that I took from UC Davis, but it really does have just a small problem. Now, alpha decay, what does it mean? We are going to produce an alpha particle. So whatever our initial nucleus was is going to lose a nucleus of helium, so it's going to have 4 nucleons that are going to be removed, 2 protons, and therefore the resulting daughter nuclide is going to be the original mass number minus 4 and the original atomic number minus 2. All right. For beta decay, we're going to lose an electron. All right. So that does not have any nucleons, so it doesn't have a just 0 on the top. But because a beta decay happens by the breakdown of a neutron, we're going to basically say, like if it had been a -1, we have actually added a proton, and so we create a -1 over here. So the daughter nuclide is going to have the same atomic mass number, but an increase of +1 in the atomic number. Gamma decay does not change the actual structure of the daughter nuclei. It just has less energy because the gamma ray is just electromagnetic radiation. Positron emission is the opposite. All right, a proton is broken down, becomes a neutron, and so we're going to decrease our Z by 1. All right, and electron capture, notice it's opposite. The electron is in the reactant side, and so we're going to end up with a product, okay, that has the same mass number but has 1 less proton inside. So how does that really look like? Here are examples. All right, we're going to make sure that we conserve both the mass number A and we conserve the Z, which is our atomic number. All right, so in this particular case, if we have a capture of a neutron, at the top we are going to have 235 plus 1 is 236. So these numbers must add up to 236, 136, 38 plus 96 plus 2, because there are 2 neutrons, is equal to 236. At the bottom, we must conserve as well our number. Okay, so we see that we have 92 plus 0 is 92, so 55 plus 37 plus 0 must be equal to 92. All right, so on the next page, I've given you a couple of exercises, and I'm just going to fill out this very first section over here. You can practice a little bit on the other side, and then we'll talk about the decay series. But just to show you very quickly what we would put there. For the first one, we can see that there we have 242, and there are 4 there, so this must be a 238. At the bottom, we have 94. We have 2 over here, so this must be 92. So it adds up to 94. And when we look at the periodic table, element 92 is uranium. All right. We have 32 for our atomic, so our mass number plus 0 is 32. So this must be 32 at the top. 16 minus 1 is 15. We put 15 at the bottom. Element 15 is phosphorus. We have 252 plus something must give us to 3 plus 2 59, so that's 262, all right? So this must be 10. At the bottom, we have 98 plus something, must be equal to 103. So at the bottom, we have to have 5. When we look at it in the periodic table, that is a boron 10, all right? Then 55 gives the 55, at the top is 0. 26 gives us 25, so the bottom must be minus 1, so this must be an electron capture. And finally, 15 gives us 0 over here, so it must be 15. And 8 is something plus 1, so it must be 7, which is a nitrogen 15. So try up the other equations that you have on the right side of the screen, all right? And we can continue. Now, if you have multiple events taking place, we sometimes write what is called a decay series. Here you can see how uranium-232, by emitting an alpha, becomes thorium-234, emitting a beta becomes protactinium-234, emits another beta, it becomes uranium-234, which emits alpha. I'm not going to walk you through the entire thing, but you can see how every time, if we add the particular particle that is being emitted and that's been written in for shorthand over the arrow, that means it's been lost, we can kind of see how we go from a particular radioactive species to a stable species such as lead-206. All right. Normally, a decay series is a series of different nuclear decays until we get to a stable configuration, nuclear configuration, in which the atom will then no longer emit radiation. All right. Excellent. So, what is another part of this numerical or more physical part of medicinal nuclear chemistry? All right. One of the things that we talked about briefly was the idea of half-life. Half-life, or T1 half, all right, is the time required for half of the activity of a substance to decrease. All right. So basically, half of the material that you have has decayed and become a different element, to become the daughter nuclide. All right. So half-life, or the process of nuclear decay, is a first order process. Okay, so let's make sure that we highlight that. Which means that it depends on the amount that you originally had. So it is going to be dependent on that, quote, concentration. In this case, it's not concentration, but the actual number of nuclides that you initially had in there. All right. But because it's a first order process, the half-life is a characteristic constant. So for every single radioisotope, those have a characteristic half-life that does not change. That value is independent of temperature or any other thing. So it's not like a normal chemical reaction where other things can affect the process. The half-life is independent of temperature, all right? The only thing is that determines the half-life is the identity of the nuclide, okay? How to find the half-life? Well, you just look at the activity of a substance and you see how long it takes for it to halve. So here we go, and we were at 80, all right? Here's 40. Here's 20. How much time happened? 2. Each single time we can see that it went down by 2. Again, we go from 20 to 10. Again, 2 more days passed by. All right, you can see it over here. So we can see the half-life for that first graph is 2 days. All right. In this other particular one over here, we can see that the half-life happens to be about 7 seconds. All right, because every time that we go to 7 seconds, we have an activity decrease of half. So those are things that are very easily determined from a graph. Concentration or activity counts per minute is one way in which we measure activity versus time. And so it's relatively straightforward to find the value of half-life. All right. So here you are. You can look at different ways in which we measure activity. It can be measured in becquerels or other units. Okay. So always find what a particular value and half that amount, and you should be able to measure that time, and it should be a constant. All right. The second thing that we want to talk about is what is the rate of decay. So rate of decay is not the same thing as half-life. Remember, rate is change over time. Okay? Now that is going to be, the rate is first order, so it's going to depend on how much you had initially. So it's going to be the change in the number of nuclides, delta capital N, all right, over time. It's going to be a negative value, delta N. So we put a negative in front of it to make this rate a positive value. So don't worry too much about the negative. It's just, all you need to remember is that our rates are always measured positively. All right. Now, as we did for any rate law expression, all right, it is the change of the substance over time or equal to some constant. In this particular case, we're going to call it lambda, and we're going to call that lambda the decay constant. Again, I'm going to highlight that name. Lambda is called the decay constant. All right, and we are going to build something like we did for the rate laws. All right, the derivative rate expression can be constant lambda times the initial concentration or initial number of nuclides that we had, capital N sub O. All right, or capital sub naught if you want. No. So if we take an integration, and you do not need to worry about being able to reproduce the interactions of the here, it's just so we can see how we can manage. All right, and I'm just going to go through this relatively quickly. All right, we look at the integration of this, and we can find the concentration, the number of nuclides that are left over at any particular time. Okay, that is going to be equal to N sub T. Number of nuclides at time T is equal to the number of nuclides initial times the natural exponent to the minus lambda, rate, the decay constant, times T, the time that has passed by. All right, so you need to make sure that your units must be equal both in your decay constant and the time in order to get the correct answer. If we want to know when this becomes half the original amount, okay, we can get an equation for finding out the half-life of a particular substance based on its decay constant lambda. So T1/2 or half-life is equal to natural logarithm of 2 over the decay constant. Or in other ways, if we rearrange this equation, the decay constant is equal to natural logarithm of 2 over the half-life of the particular substance. All right, so there are three equations, or two if you want. The last two is just a rearrangement of the same equation. But these two equations or three equations are going to be very useful in order to do this. Now, will the IB require you to deduce these equations? No. So it's much more useful for you to be able to just memorize them, use them. All right. So in your data booklet, underneath table number 1, all right, where you have all of your reactions. In fact, if you look under D, all right, it has another equation. We will talk about that other equation in a moment, but it's not a great equation. But interestingly enough, if you look at C3, all right, you will find both of the equations that we have here. N at time T is equal to N sub O, the natural exponent base negative lambda T, and the expression for half-life. So your data booklet has these equations. You do not need to memorize them, but you just need to know where to find them, all right, and what they mean. All right. So again, N sub O is the initial number of nuclides that you have, and so you can find out this. So it means that we need to apply our either we're going to use a percentage there. That's fine, out of 100%, which would have been 100% here. Or we can use the actual number of moles or number of actual species, Avogadro's number, etc., that we had originally there. Okay? So here are a couple of ways in which we can use this. If we have a question where they tell us the half-life of technetium, the mesostable technetium-99 is 6 hours, well, calculate the decay constant and how much left after certain amounts of time. All right, well, easy. All right, if this is 6, lambda is equal to natural logarithm of 2 over 6 hours, which gives us this particular value, 0.116, all right? Hours to the negative 1. 1 is a fraction of that half-life, so it's not particularly easy to determine. So we're like, okay, well, we're just going to go ahead and use our equation. All right, we enter all of our values in there, and we're going to get that is about 89% that is left over after 1 hour. All right, if we have 12 hours, that is 2 half-lives. So instantaneously, we should be able to answer 2 half-lives. It's 50% after 1 half-life, 25% after 2 half-lives. If you actually do this numerically, you're going to get 24.9. Why? Because this value over here, the decay constant, is rounded up. Okay? If you had 48 hours, which is 2 days, 48 hours is also a multiple of 6. All right? You should be getting half to the 8th, which is the real value. But because, again, we have used our decay constant as a rounded up value, and we use just the right number of significant figures, you're not going to get quite the same number. Okay? So, how can you avoid those little differences? If the number is an exact multiple integer, all right, of your half-life, then you can use this modified equation, which again, that is in your data booklet under D8, all right? Under in table 1, all your equations, all right, it's going to be there under D8. So you can just calculate it directly, all right? So not a big deal. I've put 2 problems there for you to try to practice this, all right? And that's basically it. I just wanted to make sure that we separated the, here's the one problem, here's the second problem, separated the medicinal part from the more physical and calculation section of it, so you can play with both bits of the information. All right, good. Thank you so much, and we will finish up with the last video.